We're going to be talking about something called greatest common factor. Now, sometimes for shortcut, they'll put GC out instead of writing out greatest common factor. Now, let me ask you this. True or false? 2 is a factor of 10. Is that true? 2 is a factor of 10? 2 is a divisor of 10. Yes. If a number is a factor, it's also a what? Divisor. If you can multiply 2 by something to get 10, that means when you take 10 and divide it by 2, you're going to get a whole number. So one's just looking at it out of multiplication and one's looking at it out of division. It's a little bit like if I'm standing next to this chair, some of you might say the chair is to the left of the teacher. Some others might say the teacher's to the right of the chair. Depends on what you're looking at. Are you using this one or this one kind of as your start? It's the same way here. And the reason I'm telling you that is this. Instead of putting greatest common factor, some books will call it greatest common what? Divisor. Okay. Now, I'm going to call it greatest common factor. But your book calls it greatest common divisor. And I'll explain later why I like greatest common factor a little bit better. All right? Because there's an F and not a D. See, when we start doing fractions in a little bit, in a week or so, you have to have a common denominator. But see, that's GCD. Does that make sense? And it's not a factor, it's not a divisor, it's going to be a multiple. So I don't want them to get least common denominator confused. You see what I'm saying? I don't want them to get the D's and denominator confused with the D's and divisor. So that's the reason I think greatest common factor makes a little more sense. Now, we're going to talk about different ways of doing this. All right? And you've got to know how to do all 3 of these ways for a test. Now, I would start, remember I'm going to start with what I think is the most concrete and then move to the most abstract. So every time we're teaching something, that's what we need to do. We need to go from the most concrete and then move to the most abstract. Okay? Now, guess which method I'm going to use first? Which method do I always end up using first lately? Sets. Okay? This one's going to be called intersection of sets method. Intersection of sets method. Now, disappear from the Zoom for a second to grab something. All right. I just want to show you what the manipulative in your book looks like. All right. They show you a picture of these in your book. These are called Cuisenaire rods. All right. So I've got all these rods and they're different colors and they're different lengths. All right. So there's a picture in your book on page 212, especially if you're on Zoom. Okay. Now, it's hard to see, especially if you're on Zoom, but the people in the room, do you see these little cubes? What do they look a lot like? Base 10 cubes. That's really what they are. All right, so what happens is this. These are still a 1. They were a 1 in base 10, and they're still a 1 in this. All right? So what happens is, how do I know what this red one is? Well, it depends on how many of these base 10 cubes make it. It takes exactly 2 of these little cubes to make this red. So if this is a 1, what's this going to be? A 2. All right. These little lime green ones, so to speak, if you try to line them up, it's going to take exactly 3 of these little cubes. So that means this lime green rod stands for what number? 3. So what they're saying is they're going to do what I'm going to do right here, but they would do it with these concrete manipulatives first. Okay? So here's what they would basically do. They would grab, like, for instance, maybe a black one and maybe a yellow one. And they would try to see what's the biggest one that would fill up this one and this one. Like, I know I can do it with the cubes, the little bitty cubes. But I want to know, maybe we'll take exactly 3 of these red ones here, or 3 of these red ones here, and 4 of these red ones here. So that means that 4 would be a factor of this one and this one. Is everybody with me? Now, they show you kind of in your book. Do you see their 6 rod is their lime green one? Well, actually, it's their dark green one. It's hard to see in the book. So what they're showing you is this dark green one, it takes exactly 3 of these red ones.
But the red ones are 2?
The red ones are 2. So what do I know is a factor of this one? I need 3 of these 2s. So if the red one makes it exactly, then 2 is a factor. Then they grab this brown one. And they show you that on this brown one, it takes 1, 2, 3, 4. And it's exact. So red is a factor of the brown and red is a factor of the green. So what is red? We said it was a 2. They try it with all the other rods and it won't exactly fit. So the biggest one that fits both is the 2. Now, when they're doing it, by the time they get to this, usually what I would do with younger kids is I would probably, if I could get it to work this way, but I got people on Zoom, I would use the Elmo and show them that. Is everybody with me? We would try different ones. Because you're in college, and even by the time they get to you probably in 3rd grade, most of them understand this. If I want to find the greatest common factor, say between 12 and 16, what I'm going to do is I'm going to write out all the factors of both. Okay? So I'm going to write all the factors of each one. So give me all the factors of 12. What gives me 12? What can you multiply together and get 12? 1 and 12. Now watch what I'll do. I'll jump up here and put 12 so I don't have to rearrange them. Everybody with me? What else will give me 12? 2 and what? 6. What else gives me 12? 3 and 4. Are those all the factors of 12? So there's my set of factors of 12. All right. What are my set of factors of 16? What gives me 16? 1 times what? 16. What else? 2 times 8. Anything else? 4 times 4, right? So there's my set of factors of 16. So do you understand what I mean by write all the factors? All right. Step 2. Find the common factors. In other words, aren't you doing the intersection of the sets? What they have in common, right? So what do they have in common over here? They both have a what? 1. And what else? 2. What else? A 4. Anything else? So my common factors are going to be 1, 2, and 4. We good? Now, what do I want? I don't want the common factors, I want the what? Greatest common factor. So what's my answer gonna be? 4. Why? Because it's what? Just the biggest. All right, so you're gonna select the largest common factor. Okay, so the greatest common, if I could write, the greatest common factor of 12 and 16 is, okay? So you try this for me. Then you find me the greatest common factor between 24 and 36. Use an intersection of sets. Okay. Now, what are all the factors of 24? You had 1 and 1. 24. What else did you have? 2 and 12. What else? 3 and 8. Anything else? 4 and 6. We good? So that's all my factors of 24. What are all my factors of 36? 1 and 1. 36. What else? 2 and 18. Very good. What else? 3 and 12. What else? 4 and what? 9. And what else? 6 and 6. So I write down the sets of the factors of each. All right, what's the next thing I do? Find the ones they have what? In common. So what are my common factors going to be? 1. What else? 2, 3, 4, 6, 12. Is that it? How do I know what to pick for my final answer? It's the biggest one, so what's it going to be? 12. Now, the reason I start with this method is very concrete. Even without the Cuisenaire rods, it's to me really concrete. They see it, okay? So it's easy to do, but tell me a problem that you foresee. What's the problem with doing them all this way?
You don't know all the factors.
Do what, Anna Jane?
You might not know all the factors.
You might not know all the factors. It might be that you listed them all, but you forgot here 3 and 12. So then you circle 6. So one of the issues is you have to be able to list all the factors. And the other one is, what if the numbers get really big, like 360? That's a bunch of what? Factors. So even if you can list them all, it gets to be really long and tedious. Okay? So I like starting with this, but I don't like ending with it. Okay? So let's talk about the second method. All right? The second second method is gonna be called the prime factorization. Okay. All right. Prime factorization. All right. Now, so the word implies I'm going to have to write the what? The prime factorizations of things. That's one of the reasons you learn to do that. So step one is going to be write the prime factorization of each number. And I'm going to put use factor trees if necessary. I mean, I'm not going to have to make a factor tree for 6. I would just know the prime factorization of 6 is just 2 times what? But I'm not going to know the prime factorization of 24. So that's why I said you need to use a factor tree to figure it out, use a factor tree. Okay? I want you to circle the matching factors in the prime factorization. Now you'll see what I mean by that in a minute. It's kind of ambiguous. All right. Of the numbers. So I'm going to put in parentheses, look at the bottom of the trees. And then what I want you to do is multiply the circled numbers on the bottom of one tree. Now you write that down there and then I'll show you what I mean. All right, let's go back and do the ones we've already done. Okay, we found the greatest common factor between 24 and 36 using intersection tests just a second ago. What if I do the same problem but I do prime factorization? So what I need you to do is I need you to make a factor tree for 24 for me, and then make a factor tree for 36 for me. All right, give me 2 factors of 24. What are 2 factors of 24? 4 and 6. All right, are both of those prime?
No.
No. All right, so I've got to break them down. What gives me 4?
2 and 2.
2 and 2. What gives me 6?
2 and 3.
2 and 3. So do we understand that the prime factorization is 2 times 2 times 2 times what? 3. That bottom is your prime factorization. The order might not be what Dan wants it, but that's the prime factorization. Okay? What are factors that give me 36?
6 and 6.
6 and 6. So what gives me 6?
2 and 3.
2 and 3. And again, if I just said write the prime factorization, you'd have to write 2 times 2 times 3 times what? 3. But that's not the end question here. Is everybody with me? So this bottom is the prime factorization of 36. 2 times 3 times 2 times what? 3. So that's what I mean by write the prime factorization of each number. It's just what's on the bottom of the trees. And look what it says. Circle the matching factors in the prime factorizations. Now, what do I mean? I mean it's got to match from here to here. Not in the same tree. Like there's a 2 right here. Is there a partner over there that matches it? Then circle it. All right, so there's a 2 here that matches a 2 there. There's a 2 here. Is there another partner over there that's a 2? All right, so circle them. All right, there's a 2 here. Is there another matching partner over there? No. There's a 3 here. Is there a partner matching 3 over there? So it doesn't matter if I circle this one and this one or this one and that one. Everybody with me? I just got to match one. Now, is that everything here that matches everything there? We're good? So look what it says. Multiply the circle numbers on the bottom of how many trees? 1. Does it matter which tree you look at? No, because the same things are circled. Okay? So what am I going to multiply together? 2 times 2 times 3. Okay, what is 2 times 2? And what's 4 times 3? Is that what you got a minute ago for your greatest common factor? We okay? So let's do one that's a little bigger. All right? So what if I said, find me the greatest common factor of 80, do this, 88 and 120. See, I don't want to really list all the factors of 120. So that's why the intersection of sets might not be as good. So find me the greatest common factor between 88 and 120 using that prime factorization method. Look and see if the bottom of your trees match the bottom of my trees. The order might be different, but we should have the same factors. Are we okay? So I just used 8 times 11 and then broke 8 down into 2 times 4. 4 wasn't prime, so it got broken down. Now, like I said before, don't leave things dangling up here. Okay, if it's prime, you bring it down all the time. That way your prime factorization is on the bottom of your trees. Now, there's a 2 on the left. Is there a 2 on the right that will match it? All right, so they get circled. Can I circle another pair of 2s? Yes. Can I circle another pair of 2s?
Yes.
Yes. Can I circle another pair of 3s? No, no partner. 5s or 11? No. Now, what do I multiply together? How many trees? Just 1. So I'm going to multiply what? 2 times 2 times 2. What's 2 times 2? What's 4 times 2? 8. So the greatest common factor of 88 and 120 is what? 88. All right, everybody okay? All right, we got one more method on greatest common factor, and then we'll talk about multiples for just a second. Now, this one you probably have not seen before. I don't know why, but it's a really nice method, but it's pretty abstract. It's Euclidean. called the Euclidean algorithm. All right, Euclidean algorithm. It's real efficient, but it's pretty abstract. Okay. Now, I'm going to write the steps down, and then they're not going to make a lot of sense until we do them. Okay, but I want them written in your notes first so you can follow the steps when we're doing it. The first thing you're going to do is you're going to divide the larger number by the smaller number. All right. If the remainder is not 0, you're going to do another division problem. Using the remainder and the divisor. Okay? If the remainder is not 0, you're going to do another division problem using the remainder and the divisor. And I'm going to put in parentheses. Do larger divided by smaller. Okay? You are going to continue the process until the remainder is 0. The answer, in other words, the greatest common factor, all right, is the divisor. You might want to underline that. Let's put the last divisor. That'll make a little more sense. Because it's going to seem a little weird. Now you write those steps down because I'm going to switch boards, especially if you're on Zoom. You won't be able to see the steps. Now we're going to work some problems like this. We're going to work the same problem we worked the other way so that you got it work all 3 ways in your notes. All right, here's what I want to think. If I will, again, somebody said find the greatest common divisor between 24 and 36. But this time they said I had to use Euclid. All right, what am I going to do first? What am I going to divide? 36 by what? 24. Okay? How many 24s can I pull out of 36? Just 1. So when I subtract that 24, I'm going to have 12 left. Now, is my remainder 0 yet? No. So I've got to do another division problem. Which 2 numbers am I going to keep using from this point forward? The what? The remainder and the, so what's my remainder? 12. What's my divisor? So I'm always going to use the remainder and the divisor. Now, this is not like when you were doing other bases, you were drawing blanks. Okay. This one you are going to do bigger divided by what? Smaller. So what am I going to divide? 24 is going to get divided by what? 12. Now, I can't pull any 12s out of 2, you know. Like how many 12s can I pull out of 24? I can pull what? 2. Now, here's where people can get confused. How do I know to quit, first of all? How do I know I'm done? Remainder 0, but don't pick the wrong answer. What's the answer? It's the last what? Divisor, not the quotient on top. Okay? So that means that my last divisor right there is what number? 12. So sure enough, isn't that what we got a minute ago? That's the greatest common factor between 12 and 36. Okay? So why don't you try that other one? Why don't you try to find me this? The greatest common factor between 88 and 120. We worked that one a minute ago, using prime factorization. Now you try it using greatest common factor. Which one am I going to divide by what? What am I going to write down? 120 divided by 88. Okay, I can't pull any 88s out of 1. I can't pull any 88s out of 12. How many could you pull out of 120? 1. What was your remainder when you did that? 32. Now, how do I know I'm not done? I don't have a remainder of 0. So what two numbers am I going to grab? The remainder and the divisor. So they keep being smaller numbers anyway. So which one do I divide? Bigger by what? Smaller. How many 32 did you pull out of 88? 2. That was 64, correct? So what was your remainder? 24, wasn't it? All right, so again, I don't have a 0, so I'm going to use the remainder and the divisor. So 32 divided by 24. How many 24s could you pull out of 32? 1. So that left you with how many? 8. And again, I don't have a remainder of 0, so I got to keep going. But 24 divided by 8 is what? 3. And again, how do I know to stop? Remainder of 0. But my answer is not 3. So we're used to looking at the answer for the division. I know that's for the answer to the division problem, asking for the greatest common factor, so it's the last divisor. So I got 8. Okay. Now, this one is especially good if you start getting really big numbers. Like sometimes they'll have something like 1,248 and 893. Well, there, I sure don't want to be listing out all the factors and intersection sets. And even my factor trees would start getting really big. So when the numbers are larger, this one comes out to be especially handy. Now, when you take a test from me, what's going to happen is sometimes I'm going to tell you which method you have to use. So you do have to be able to do all 3 methods. All right? Because you can't teach it if you can't do it. And some students like one, some like the other, so you got to be able to do all 3. Now, if I just say, find me the greatest common factor between these 2 numbers, then you can pick your personal favorite. Okay? But you do need to practice all 3 methods so you're okay on a test with all 3 methods. Okay? So is everybody clear about kind of what factors are? Now, I just want to do one method real quick on talk about multiples for a second, just so we're ready on Monday. I mean, on Tuesday of next week. want to know what's the biggest factor that works. So greatest common factor. But then we want to know about the least common multiple. And again, they're probably going to abbreviate it like LCM, least common multiple. Now, we talked about this over and over, but you're going to tired of me saying it. Oh, well. Okay. Are multiples bigger than the number generally or smaller? They're bigger. So the only intersection that factors and multiples have is the number itself. So except for the number itself, factors are smaller. And except for the number itself, multiples are bigger. So what do you think the first method is going to be? They're going to do sets, that's right. So again, it's going to be intersection of sets. Intersection of sets method. Okay. So step one is going to be a little different. Can you list out all the multiples? You have to list all the factors, but can you list all the multiples? No. So here's what I'm just going to say. List multiples of each number. Now, did I tell you how many to do? No. So I list some of the first one and what? Some of the second one. Because here's what you're looking for. I'm not looking for the biggest. What am I looking for? The smallest. So as soon as I find one that matches, what can I do? Stop. When you find a multiple that matches, stop. And your answer, in other words, your least common multiple is that number. Everybody okay? So what if I said find the least common multiple between 6 and 8? Now, here's what I would like you to do. Because I get this a lot on the test. I don't want you to confuse the greatest common factor of 6 and 8 with the least common multiple. So before you ever start, I want you to zero in, is it a factor or a multiple? With a factor, you just told me, are factors generally smaller or bigger than these numbers? They are what? Smaller. So you can't get a 48. Just like up here, multiples are generally what? Bigger, so I can't get a 2 for the answers. Everybody with me? So don't confuse. Don't worry about the L and the G first. Worry about the F and the what? The M. Am I doing factors or am I doing multiples? What am I doing up here now? I'm doing what? Multiples. So I'm going to be listing multiples of 6. All right. So what's the first multiple of 6? 6. What's going to come next? 12, 18, 24, 30. I mean, everybody with me? Come down here and do 8. What's your first multiple of 8? 8, then what? 16, then what? Do I need to keep going? No. Now, if you want to, I guess that's fine. You're having a great time. All right? But as soon as you find one that matches, you are finished because you want the least one. So my least common multiple is what? 24. Now, I remember when my son was doing problems like this, he was at the table, he worked their problems almost just like this, and he kept going. I'm like, okay, now I'm going to get it. I said, what are you doing? He said, I'm finishing. You are finished. No, I'm not. Ms. Jones told me to write 6 of each. All right? If you tell a kid to write 6 of each, they're going to write what? 6 of each. Now, she meant it just like a guideline. Everybody with me? In other words, try 6 or so and see, but kids are going to take you literally. So make sure that you make it very clear where this is a rule or this is a guideline. I mean, I still remember one of my students told me this one time. Her daughter came home from school and she was writing her name in the most bizarre manner. Just crazy. And when you have a bunch of kids, you just don't care. You know what I'm saying? You're like, she's dressed, you're not hungry, the cops aren't coming. So she just ignored her. But finally, after a few days, her mother could not take it anymore. So she said, "What are you doing?" And the mother told me later. She said, "What are you doing?" So their daughter said, "Writing my name." And she said, "Why are you writing your name like that?" And she said, "The teacher told me to." She said, "The teacher did not tell you to write your name that way." Yes, she did. Once again, you're having that conversation with your kid. No, she didn't. What did she say? She said, "Write your name so I can read it." Now, here's what happened. The kid was sitting in a desk in front of her, like say Amber is. The teacher was standing in front.
Oh my God.
She wrote it upside down and backwards. I don't know how a kid can do that. You know what I'm saying? Like, I couldn't do it unless I literally, she was writing her name upside down and backwards because the teacher said, "Write your name so I can what? Read it." So when I tell you they take you literally, they take you what? Literally. Okay, so I just, God bless you. You know what I'm saying? Like, you go, girl. I couldn't do that if my life depended on it. Now, why the teacher had not said something to this point, maybe she hadn't taken a paper up or something, I don't know, but I'm just like, wow. But there are a million stories from teachers and parents to me like that. And the younger they are, the more literal they will take you. So you've got to be real careful with just what I call kind of off-the-cuff remarks. All right? They will literally jump through hoops to please you. And sometimes when a kid's doing something, you might want to ask them why. Okay? So I'm just saying. Now, where's your homework going to be? On Google. And we kind of know what our tentative test date is. All right? So I will see you next time. If you need some help, come see me.